Okay. Are there non-colored short? These are very... This looks kind of... Okay, I can start with this. That's great. Thank you. Thank you very much. Good. Thanks for the invitation. Just a disclaimer, I'm a geometer. I will not intentionally talk about F-theory. If I end up talking about something that's relevant, that's great. So actually, my goal is to get you interested in some kind of singularities that maybe you haven't seen before, but I'm hoping that maybe it is relevant to your interest. So let me talk about conical transitions as I understand them. So let's say start with a okay. So compact complex manifold, and I'd like to imagine this embedded into projective space, some projective space, or the complex numbers, and then look at the cone over this. So let's say this is y, and then this projective space has a projection from some larger affine space, or if you want just write this, I'm primarily an algebraist, so I tend to do that. So we have this cone, and so I'd like to concentrate on this singularity here. And if you have something singular, we'd like to make it non-singular. And there are at least two ways to do this. And in the case of a cone, so we have that projection. So if I look at the cone that's outside of the vertex, then I have a projection to the original y. So let's say x is my cone over y, and so I have a projection, and I want to look at this as a map and the graph of this. So the graph of this projection, just the points x, y, where x maps to y, and so this lives in this product space. And I want to look at the closure of this inside when I put the vertex of the cone back. And so what do I get? Well, if I look at these projecting lines, so for each line, I get the same y. So for each point on the line, I have the same y. And when I look at the projection, then these lines kind of get separate. And so what I end up with is, so I have this cone, and for each point on y, I get 1 point over the original cone, or of the original vertex. So I have something like this, where this is not going to be a cylinder. It's a cylinder up to this point, but there's kind of a rotation there. So it's sort of more like this. But I usually I normally draw this, but I don't want to give you the impression that it's a cylinder. And this has a map to the original cone. Because obviously this can be projected to X. So I have this map. And of course, I'm doing the cone this way, but it's kind of like that. Okay? And let me make some room here. So this is, in math, in geometry, we call this a resolution of singularity. So if you're familiar with ADE singularities, then you must have seen this. This is usually just a rational curve, a sphere with some complex structure, and then this way you get an ADE singularity. But there's nothing to hold you back to do this for an arbitrary y. Okay, so this is one way to remove this singularity. And another way is to what we call smoothing. Namely, imagine that your y is, let's say y is a hypersurface. So it's defined by a single equation. Then this cone is also a hypersurface. It's defined essentially by the same equation, except that here we're thinking of it as a homogeneous equation, and here we forget that it's homogeneous. So if you have a single equation, then perturbing it a little bit gives you something non-singular. So what you do here is, so what would happen if I perturb the equation? Then I would have something like this. And, well, let's say that if this is really far from the perturbation, then here I don't really see what's changing. So this here, it looks kind of similar, but at the singular point, I made it non-singular. Okay, and so as far as I understand, the conical transition is essentially relating this resolution of singularities to this smoothing. Okay, so this is my main object, and so I would like to understand what's happening when, so what's happening when y itself is a Calabi-Yau. Okay? So I want to say y is a Calabi-Yau, and I want to understand the singularity. I want to understand the relation between these two objects. Okay. So what can we say about the singularity if y is a Calabi-Yau? So in fact, let's just start with the fact that if y is a Calabi-Yau, then it's Ricci flat. And so the canonical divisor or bundle or sheaf, I don't know which one is your preferred terminology, but this is trivial. Okay? And now, if I have a map from this resolution of singularities, I can take that, I like to think of, yes?
So your definition of Calabi-Yau here will just be...
No. So my definition of a Calabi-Yau, okay. So I would like to say that this holds, and I would like to say that H1I is 0 for I larger than 0 and smaller than the dimensional y. Is this a good notation? So for algebraic geometers, I would say Hi of OY is 0 for
H1I or 0? I mean 0.
0.
Oh, 0, sorry. I'm sorry. Does this agree with your definition of covariance? Or one possible definition?
Yes.
Okay. Yes. Okay, so this is my definition of caveat, but first I just want to concentrate on this condition. And so basically I would like to, okay, so this cone was X, and let me call this guy X twiddle, and let's say this smoothing X prime. So I would like to compare the canonical of X twiddle to X, to the canonical of X. So first of all, so I have this resolution of singularities for X, and so I have a canonical on X twiddle, and I have a canonical on X, and I can pull this back. So by pull back, I like to think of it as just a bundle. So pull it back as a bundle. If you want, you can think of differential forms and just pull back those differential forms and compare them to differential forms there. I would like to see the difference. Well, the difference, well, outside of this guy, this is just an isomorphism. Nothing happens outside of the vertex. And let me denote this by E for exceptional. So what's happening with this resolution of singularities is that this E gets collapsed. So E is collapsed to the point, to the vertex. Okay? And so now what happens if I'm thinking of this as divisors, then the difference between these two will be a multiple of that E. Right? So the way I'm thinking of this is, say, take a differential form on X, and then pull it back to X twiddle, and compare it to a differential form there, and this might pick up some poles along E, or might pick up some zeros. Okay? And this A is the number of times it picks up a zero. So it's either zero or pole, so it could be positive or negative, but it tells me what's happening. Okay, now what do I know? How can I determine this E? Well, what I know is that this E is actually isomorphic to Y. And I'm using a different letter, as I want to emphasize that this is actually differently embedded into X twiddle than the original Y. This original Y is a hyperplane section, and this actually moves inside X twiddle. This E is rigid inside X twiddle. It's the fact that it's collapsed tells us that you cannot move it inside X twiddle. Okay? In fact, if I take the line bundle corresponding to this E, and restrict it to E, then I get something negative. Okay? And on the other hand, it's also a complex manifold, so it itself has a canonical bundle. And the adjunction formula tells me that this canonical bundle can be computed by taking the canonical bundle of the ambient space, twist it with E, and then restrict that to E. Okay? And now, what do I have? I have this, and I have one more fact, which tells me that when I pull this canonical bundle from X and restrict that to E, so again, I take a differential form here, pull it back here. If I restrict it to E, what happens? Well, it will be trivial because E is collapsed to a point, so there's no variation will actually show up on E, so this is trivial. So now I have three equalities, and if I compare these, so basically I can substitute this here, and then I substitute this here. So I have here, I have pi per star of kx plus 8 times e. But pi per star kx restricted to e is trivial. So this tells me that ke is a plus 1e restricted to e. Okay, now what does this tell me? Well, I just told you that e restricted to e is negative. But I know, so I want to assume that y is Ricci flat, which means that e is Ricci flat. So this guy has to be 0. So the only way this will happen to be 0 is if a is minus 1. Okay? So this is telling me that the kind of singularity here that I get is a little bit more complicated than the ones that you may have seen before. So it's more complicated than AD singularities. Okay. So let's talk a little bit about singularities in general. So let's say I have a singular space, and then, oh, I just realized that I denoted 2 different things with pi, but no one complained. So, and I erased the first notation. So pi is going to be what is still on the board. So this is pi. And I just erased the other one. Anyway, so let's say I have a resolution of singularities. And again, I can do the same kind of game that I can compare the canonical of the resolved guy and the pullback of the singular guy. And for simplicity, let me assume that there's only a single exceptional divisor. So in that case, again, I have something like this. And as we see in this computation, the coefficient here is actually telling me something about the singularity. Okay? And so if you're thinking of ADE singularities, then in the ADE case, one of the conditions that we have here is that B is non-negative. Okay? So the more general definition is that a singularity is called canonical if this holds. So this is in arbitrary dimension, and it could be a little bit more complicated than an ADE singularity. And now, in our case, we see that this is not canonical, but this is still something that we can manage, and this is called log canonical. So a log canonical singularity, so one way to say what a canonical singularity is that if you have a differential form on this singular variety and you pull it back, it does not pick up poles, that it remains regular. Okay? So one way to write this, that B is non-negative, is that, so this is kind of like saying that when I pull back KZ, this will not beat KZ fill, right? Because I have something effective here. So log canonical does not have this condition, but it still has the condition that it can pick up at most a simple pole. So it doesn't get too much worse, and so log canonical has the property that there's only at most of one here.
What's the use? Why is it? motivation for the word log?
The log. Okay, so this is not entirely obvious or debatable, but essentially, well, it's basically this +1 that.
Log means +1?
So.
You allow a simple pole in the holomorphic form.
I'm sorry?
You're going to allow a simple pole for the holomorphic form.
Right. So if you look at. So if you say something like df over f.
The integral is log.
That's right. So. But also. So sometimes when we look at manifolds with boundary or an open manifold, and then look at pairs, so something like z comma say d, and then you look at log differential forms with logarithmic pole around here, and so the actual definition of canonical and log canonical is usually for pairs. And yeah, does this answer your question? So essentially, I would like to get you interested in this class of singularities. And so how does that relate to conical transitions? So we have this computation that tells me that if y is a Calabi-Yau, then this will be a log canonical singularity. But we can actually say more about the singularity. One of the things is that a very useful property of a singularity is something called rational. So there are so-called rational singularities. And the simplest rational singularities are the ones when you contract a rational curve. So, for example, ADE singularities are rational, and the general definition is that, again, okay, I'm killing these chalks. So, if you have a resolution of singularities, then Z has rational singularities. If the push forwards of this sheaf, the higher direct images are 0 for positive I. Okay, so essentially, in a cone singularity, this essentially means that the Y doesn't have higher cohomologies of the structure sheaf. And so if it's a Calabi-Yau, then we know that, so in our case, so we know that, let's say D is dimension of Y, then we know that in this case, the top one is not 0. Because what's happening, so I apologize for this, but I don't really know how to do this without a little bit of algebra. So on X twiddle, so this is the structure sheaf. I can look at the structure sheaf restricted to OE. So I'm looking at holomorphic functions on X twiddle, the sheaf of holomorphic functions, and restrict that to E. And then I have some kernel for that. So there's an ideal sheaf of E. So this is a short exact sequence. And now if I push this forward to X, then I get a long exact sequence. And now here I would have the D plus first cohomology of the ideal sheaf, but the relative dimension of this map is D, so there's no D plus first cohomology. So this is 0. And this one, since E gets collapsed to a point, this is just the top cohomology on E of the structure sheaf. But the structure sheaf is the same as the canonical, and D is the dimension of E. So I know that this is not 0. And so here I have a subjective map. So this has to be non-zero. Okay, so this tells me that the singularity that I'm looking at, so Y is Calabi-Yau, then this singularity is, so this is low canonical, but not rational. Which is not surprising, is this is generally known that low canonical singularities are not rational, but they're relatively close. So let me try to draw a diagram of singularities. So let's say we have low canonical singularities, and then we have rational singularities, which are, so there are rational singularities that are not low canonical, and there are low canonical that are not rational. That happens, but in the in both of these is the class of canonical singularities, and inside that you have the ADE singularity. Okay, and so between canonical and low canonical, and still within rational, there's another class called KLT, which Grassi and Wiegand suggested to study within F theory, I suppose. And now I'm suggesting to go one step further and to study low canonical singularities. So KLT is still within rational, so low canonical goes outside of that. But there's actually, between rational and the larger word, there's still one more class that I'm interested in, and that's called Cohen-Macaulay. And now, not going to tell you what the definition of a Cohen-Macaulay singularity is, because if you don't know, just telling you the definition will not change, but I can give you examples that. So for example, the most typical Cohen-Macaulay singularity is a local complete intersection, or just complete intersection, or hypersurfaces. So local complete intersection. So if you're okay studying only hypersurface singularities, then those are Cohen-Macaulay, so that's great. And as in this example, we know that there are Calabi-Yaus that are hypersurfaces, K3s, for example. So there are this type of singularities that are themselves hypersurfaces. So there are Cohen-Macaulay singularities that fall into any of those intersections or non-intersections. For an algebraist, Cohen-Macaulay singularities are really interested from, say, duality point of view. So Cohen-Macaulay singularities are kind of the right class where duality, Grothendieck duality works. So this is, I know, unfortunately, the word duality is totally overused, so you're probably thinking 20 different things when I say duality. But, so if you know what Grothendieck duality is, let me actually say Grothendieck duality is easy. And what do I mean by easy? For example, grothendlic duality reduces to sad duality in this case. So that makes it easy. Now, if you don't know either grothendlic or sad duality, then this is not a very informative condition. But let me give you a different reason to like Conical singularities. Okay, I'm gonna erase this because, and I'm probably going to immediately regret it. But so, I have about 15 more minutes, is that correct? Okay, so let's talk a little bit about moduli theory. And what I mean by moduli theory, as I said, I'm a geometer, so I'm thinking of geometric moduli. And so, for example, I mean something like MG, the moduli space of genus G remote surfaces. And let's say that you study MG and you want to do enumerative geometry. In other words, you want to do intersection theory. But in order to do this, you need compactify this space, because intersection theory only works well if your space is compact, so you want to go to MG bar. Okay, now what does this mean? This means that we actually have to throw in things that are singular. And what are those what type of singularities do we have there? Well, if you're familiar with MG bar as in the moduli of stable curves. So for curves, this is relatively easy because the type of singularities that you want to allow is very simple. So it's just simple normal crossing. Okay? But this already has an interesting phenomenon, namely, this itself is already not rational. This is not a rational singularity, kind of for a silly reason, because it's not normal, if you know what normal means. Okay, but it's still actually, it is still Conical. But I want to do this in higher dimensions. So not just curves, so these are complex curves. What if we do surfaces? What if we do threefolds? So let's say that you have a moduli space of some complex manifolds. So this is I don't want to get too specific in here, but for example, you could take canonically polarized complex manifolds. So and so MG, if G is at least 2, is an example of that. Okay, so this, if you want, this is a generalization of MG when G is at least 2 to higher dimensions. And I want to compactify this. So I have this guy, I want to compactify. And I wonder what kind of singularities do I have to allow on stable varieties. So what are stable varieties or stable singularities in arbitrary dimensions? And now this gets kind of really fast now. But how do we do compactification of moduli? Well, currently the best technology to do that is using the minimal model program. Namely, we look at a family of objects, and well, we know that we cannot resolve singularities in a family. So we can resolve the totality of the family, but we cannot guarantee that each fiber will be non-singular. But what we can do is make the singularities relatively better. And actually, the answer is that we can get a stable, compact moduli space if for stable singularities we allow low canonical singularities. So low canonical is the right class of singularities for compactifying moduli spaces. So,
sorry, what is the notion of stability here?
I'm sorry?
The notion of stability.
Notion of?
Stability, stable.
This is exactly what I'm trying to tell you. So let's say stable, the definition of stable is, okay, this is a physics conference, so it could be a little bit, let me not finish the sentence, I don't know how to do that. Anyway, what I'm trying to say is that I'm looking for the right definition of stable, okay? And one criteria for that is that if it works, then it's gonna be good. This is what I meant by a physics conference. Okay, I shouldn't get more into that, huh? Okay, so the goal is to get a reasonable compactification of the moduli. And by reasonable, I mean that I don't just want this space embedded into some compact space, that's the closure of it, but I want that compactification to be meaningful. I want it to be a moduli space of some objects that's a larger class of objects than the original one. And the answer is that if I define stable as low canonical and plus the some conditions that come from the original class, then it's gonna work. Okay, I'm lying a little bit because the definition of low canonical actually also includes being normal, which is something else that I didn't define. And already here, we know that we have to do something non-normal. So we actually have to do the non-normal version of low canonical, which is called semi-low canonical. But that's another thing that I'm not going to tell you. Thank you. And well, I can tell you this, that so semi-low canonical is usually abbreviated as SLC. If I add normal to SLC, then I get low canonical. So SLC is essentially low canonical minus normal. And if you know the meaning of any of these words, then you know that I'm really just BSing here. But the point is, you're not going to lose anything just thinking low canonical. And the point is that for us working in moduli theory, this is an absolutely good enough justification of studying these singularities. So if you want a compact moduli space, then this is the right class of singularities. And for curves, SLC singularities are exactly these. So it's an extension of that. Okay, but I told you I'm going to tell you something about Conical singularities, and also why did I talk about conical transitions of Calabi-Yau's? Well, so at least in my mind, the point of the conical transition is that it connects two different ways of making something non-singular. So you have the resolution of singularities and you have the smoothing. Now, at least over the complex numbers, resolution of singularities always exists. Smoothing doesn't always exist. So I would like to ask the question, if I have low canonical singularities, when do I have a smoothing? Okay, so let's say that I have this the conifold transition. And I would like to ask, so let's just actually stick to first to the cone case. So let's say that X is cone over Y, and Y is Ricci flat, so KY is trivial. So now here's an, okay, there are two things. So one is a very simple lemma that says that X is Conical if and only if Y is a Calabi-Yau. So this is a very simple computation in cohomology. So I define Calabi-Yau, so this is under this condition. So if you have a Ricci flat manifold, and you take a cone over that, then this singularity is Cone-Macaulay if and only if that Ricci flat manifold is a Calabi-Yau. So for example, this distinguishes between tori and Calabi-Yau varieties. So if you have a torus of dimension, complex dimension at least 2, then it will not be, the cone over that is not Cone-Macaulay. Okay. Just check that I use the CMCY. Okay. And now here's an actual result. So this is a joint result with coli. And so this is really a corollary of the result, which I will hopefully will be able to also state. But this says that if we're in this situation, if X admits a smoothing, so in other words, if there exists really a conifold transition, then X has to be Cone-Macaulay. So what we're saying is that if you have a Ricci flat manifold and you take a cone over that, if this is smoothable, then that Ricci flat manifold had to be a Calabi-Yau. You cannot have anything else. And the actual theorem is more general. So I'm going to state it just so it's, so to speak, on the record. So if you take a flat deformation and you look at the relative dualizing complex, whatever that means. I'll if you don't know what this is, I'll actually list consequences that you hopefully will. So I want to look at the cohomology sheaves of this relative dualizing complex. Oh, sorry, I need a condition first. One condition is that, so let's say I have one member of this family that has low canonical singularities. Then the following is true, that then the cohomology sheaves of the relative dualizing complex are flat and commute with base change. And now, I suspect that for many of you, this doesn't mean a whole lot. But one of these cohomology sheaves is the relative dualizing sheaf, or a bundle, if you want. So this includes the relative dualizing complex with dualizing sheaf, which now I'm using omega, and maybe you would be happier if I used K. So one of these sheaves is the sheaf that corresponds to the bundle that's the relative dualizing bundle. And so what this tells us is that if I take the relative dualizing bundle and restrict it to fibers, then I get the dualizing bundle of that. And so these are flat and commute with base change. And now, so the importance of these sheaves is that these actually measure when a singularity is Conical. And one definition of Conicaliness is that these sheaves are all but one I, they're zero. And so what this is saying is that if I have this sheaf, it's flat and commute with base change, then if I have one fiber for which all but one value of I gives me zero, then they all give me zero. And so a consequence of this is essentially this, but in a little bit more general form. So a corollary of this is that in such a, so if I have a flat family and at least one fiber has low canonical singularities, then being Conical is a closed property on the base. And this is actually surprising because being Conical is an open property which has been well known. So in other words, if something is Conical and you do a little bit of a perturbation, then it remains Conical. But this is saying that if we assume that it's low canonical, then it works the other way, that if the perturbation itself is low canonical, then the special fiber has to be, I'm sorry, if the perturbation is Conical, then the special fiber has to be Conical as well. And what this, I know I have about 30 seconds, but I think that's enough. So for moduli theory, this means that if you have a moduli space of canonical polarized varieties, then even after compactification, if you look at the connected components of this moduli space, they come in either Conically or non-Conically fashion, in the sense that take one connected component of this moduli space, then take a single point in there. If that parameterizes something Conically, then everything parameterizes something Conically, and if that single one is non-Conically, then everything is non-Conically. So for example, this actually implies that these moduli spaces are disconnected, but it also implies this smoothing criteria, that non-Conically low canonical singularities are not smoothable. Okay, thank you very much.
Questions? What's the behavior of the metric on moduli space and the limit where the volume of the exceptional?
I don't know. We know very little about these moduli spaces in higher dimensions, unfortunately. So it's even their existence is just a few years ago that it was established. So I'm talking about higher dimensions. I assume. Yeah.
Higher dimension is what for you?
At least dimension 2. So complex dimensions. So for example, a moduli of surfaces. So okay, so maybe I should clarify that. So the existence of moduli of smooth surfaces has been known for a long time, but the compactification, the moduli compactification, so I think the last bit was proven in 2011. And the existence of this compact moduli only appeared in print in 2017, I think. So my point is that we're just at the beginning of actually understanding these moduli spaces in detail.
So I must be completely understand. You're talking about Calabi-Yau case?
No. So the Calabi-Yau was the exceptional. So the
You're
Calabi-Yau.
much more general.
Yeah, so I was talking about canonical polarized. So the way a Calabi-Yau would come in is a polarized Calabi-Yau is a low canonically polarized variety. And so even that for, okay, so for K3s and Calabi-Yaus, obviously we knew a lot more. So I was talking about the
But I think the case that would be in physics more interesting perhaps would be, in addition to Calabi-Yau, the positively curved ones. Is there any subcategory for you where the singularities of the positively curved ones are distinguished?
So this is interesting. Essentially, if you do anything more so positive means kx is positive, or so yeah. So the problem.
It's like CPN, like CPN.
Oh, like CPN. Okay. So that actually works with the pair formalism. So so we can make that like del Pezzos or Fanos. If you have a polarization, then you can do something. If you don't have a polarization, then you have a problem with the separability of the moduli spaces, that there are too many automorphisms. So somehow you have to kill the automorphisms before you can do this. But those actually fall into these singularity categories. So the formalism works. Does this answer your question?
Yeah, and they're easier, presumably. I was hoping that
In some sense, yes. As long as you can deal with the automorphism. So the hardness comes from too many automorphisms. But if you can rigidify the automorphisms, then it becomes easier.
So although the moduli space of smooth Calabi-Yaus is well understood, if we're going to the singular limit, can you say again what the statement would be for sort of what classes of singularities you believe would
So
exist in this stable moduli space for Calabi-Yau?
So the singularities that you would have to allow are these SLC singularities. And so what exactly is the question?
I'm just saying, exactly how singular can I go is my question, and stay in a good moduli space.
So you can actually stay within semi-low-canonical. So that's the largest class you need to allow. And in some sense, so you can give examples that you actually have to allow those, because otherwise you don't get a compact moduli space. Antara?
So you have this, these hypotheses, the example, the guiding example was the cone, right?
Yes.
How that is, but then you dropped it, right? In the
Yes, so in the theorem, it doesn't have to be a cone.
Yeah.
But for a cone, what this theorem is telling you is that, for example, it tells you that a cone over a torus of dimension at least 2 is not smoothable at all.
But do you have more general, a handle on something which is a little bit more general than a cone of a Calabi-Yau, but not completely general. Yeah,
absolutely.
Yeah.
It's interesting. So higher dimensional examples of singularities are very hard to find that are not cones. So one possibility, which may not be very enlightening, is take a cone and then take a deformation of that. And so that's other things are what you can get is quotients, but they tend to be rational.
Right.
So it's sort of it's kind of hard to get an example like this from a quotient that's low canonical but not rational.
What is the go-to example to illustrate a singularity that does not have a smooth end?
A cone over a torus.
A cone over a torus.
That's the simplest. And it's sort of hard to imagine a cone that doesn't have a smoothing. But one reason, well, this is not a proof, but kind of behind what's going on is that we know that a torus cannot be a complete intersection other than an elliptic curve, so other than a one-dimensional one. So a two-dimensional torus can never be a complete intersection. And you know that a cone over a complete intersection is smoothable because complete intersection is a cone over a complete intersection is itself is a complete intersection. And the complete intersection is smoothable because of, Bertini's theorem. Does this answer your question? Not really?
But we talk about.
Okay.
Any more questions?
Just two quick comments. If you came in late and didn't sign our sign-in sheet, please do, so that we can tell the NSF that you came and spent our money well. And yes, and also if we can get a head count before at lunchtime for those who would like to join us for dinner.
Okay. So we're gonna wait till 11:30, and Miriam will give last talk of the morning.
I see.
I did a lot of things from your answers.
Okay.
Questions. And so if I can, we work on the adoption of similarities.
Right.
And that's when we
Right. Right. I thought of starting before saying that a lot of things I will say. Digital paper.